Welcome back. In the last lecture, we introduced the concept of psychophysics and we looked at how we can measure experience. Specifically, we came up with the concept of threshold and J&D, the Weber's law, Fechner's law, and then Stevenson's law. These are the fundamental concepts which can be applied to the entire sensation. In this lecture, we will look at the psychophysical laws, whatever we have discussed earlier, applied to visual perception. So before we go into applying these concepts to visual perception, we will look at a couple of terminologies clarified. Now let us look at how visual perception is happening. Let us break the whole visual perception into smaller steps. The first step in understanding the visual perception or any perception is starting with a stimuli, characterizing the stimuli, and then how that is relating to the experience is what we have learned in the last class, the foundations of the psychophysics. We will apply the same thing to our visual perception also. In the visual perception, there is a surface and there is an incident light, and the surface is reflecting the light, reflected light, and there is a perceiver, let us say, is seeing the object. Let us say he is an observer. So the light itself has physical properties. If you look at the physical dimensions of light, frequency, amplitude, purity. Corresponding to this physical dimensions, there are psychological dimensions. Let me call it as a psychological dimensions. So the frequency is what we call as a color. The technical name for the color is Q. Hue, not Q. The technical name for color is hue. The amplitude of the light is perceived as brightness. The purity of the light is perceived as saturation or richness. You can see that the light has a physical dimension, and after it is perceived, we have certain terminologies. Now this is only the psychological dimensions. We are going to talk about another dimensions which is called the psychophysical dimensions. Okay, these are the basic physical dimensions of the light. There are more involved dimensions of the light we will see. Another physical dimension we can say is the energy, right? Energy. That is what we call it as a light. This is what usually we call it as a light. Luminous flux. This we call it as a power of the light. So luminous flux is light energy per unit area, unit time. Light energy per unit time. And then luminous intensity, this is called a luminous flux per solid angle. Per solid angle. And then we have luminance itself. Luminance is called the light intensity. Luminance is nothing but the luminance intensity per unit area. As intensity per unit area projected on a given area and direction. This is the unit of, this is one of the main important terminologies will come again and again, so we will focus little bit on this. Its unit is candela per meter square. And then there is another property called illuminance. Luminous flux per unit area. This is what we call it as a lux or lumen per meter square or lumen per meter square. So the main difference between this and the luminance is that there is no direction involved over here. So these are the involved physical properties of the light. Some of this terminologies may be confusing, so I'll try to clarify a little bit. When we have the surface, that when the light is incident on the surface, suppose if we measure the light over here, suppose this is our sensor, the sensor measuring the incident light is called the illuminance sensor. This is incident light. So this is measuring the illuminance. That is measuring the lux. How much amount of light is falling onto the surface per unit area. That is the illuminance. When the light is reflected and the user is over here, observer is over here, depending upon the direction where the observer is, the reflected light look differently. So that property of light that depends on the direction is called the luminance. There's a light intensity. So you can see that light intensity after falling off the surface and then getting reflected coming to the observer is the luminance. How much light is coming to the observer is called the luminance. So now luminance is also called the brightness. Luminance is a physical quantity, whereas when it is perceived by the observer, then becomes the brightness. brightness is a psychological quantity, right? It's subjective. There is another term, we can also call it as a apparent. Some researchers say apparent luminance. There is also another term to capture the psychological dimensions of the light when it is reflected off the surface, is called the lightness. This also you will come across, lightness. This is called the apparent reflectance. Reflectance. So the luminance may result into two psychological parameters. Let us say it can be either brightness or the lightness. So you can see that we are trying to characterize the light physical properties and then see what are the psychological dimensions of the light. The third dimensions which we are talking about is the psychophysical dimension of light. Brightness is a psychological dimensions, but there are much more. So when you relate the psychological concepts with the physical dimensions, then it becomes a psychophysical parameters. For example, color. It is called the, in fact it is called the chromatosity. Chromatosity we will see in one of the next lectures. Contrast talks about the apparent appearance of the light when there is two different intensities are involved. Adaptation. So over a time when the light is exposed to the photoreceptors, or how its response is actually changing, there is the adaptations. These are all psychophysical dimensions of the light which we need to be aware of. So given this basic background on the physical properties of the light, psychological concepts of the light, and the psychophysical dimensions of the light, now let us look at some of the experimental data available as far as the visual perception is concerned. We will relate the experimental data to the concepts what we had seen in the last lecture about the three psychophysical laws: Weber's law, Fechner's law, and the Stevenson laws. I'm going to show you a series of graphs from which we can see the psychophysical dimensions of the light. Okay, on the slides you are seeing the Weber's law for the light intensity increment threshold. So in the x-axis you can see that in the x-axis you are seeing this light intensity, and the y-axis you are seeing the change in the light intensity that can be perceived. Basically you are talking about the difference threshold, the J and D, as we mentioned in the last class if you remembered. So this graph shows the light intensity J and D for cones separately and then rods separately. Okay, so for the cones it is 14%. Usually the J and D is mentioned in terms of the percentage. Okay, and rods it is 2.5%. So the same graph of when it is made as a log graph, you can see that is almost 45-degree slope. Both rods and cones have 45-degree slope. Only the y-intercept and x-intercepts are different. Okay. According to Weber's law, that del I by I, that is the J and D, there's a Weber fraction must be constant. So again, when you plot intensity in the x-axis and the fraction del I by I in the y-axis, you can see that there is a straight constant Weber fraction for both cones and rods. Either linear graph or log, this satisfies. In the log graph, you can see that again that's a now constant line. This graph demonstrates the intensity of the light in a very small narrow range. It is not for a very large range, it is for a very narrow range. For this very narrow range, these numbers of 14% and 2.5% and holds good correctly. But when we go over the range, these numbers change. That is what recently the researchers have come up with. So the same graph, it is shown in the next graph for a much larger range. Again, you can see that in the x-axis, luminance is plotted. Luminance, if you remember, it's light reflected from the surface. That's a measure of the light reflected off the surface. Just before the light reaches the observer, what is the amount of the light? Okay, it's a luminous intensity per unit area, candela per meter squared is what we have seen it. So that is mentioned in the log scale. On the y-axis, again this fraction is Weber fraction is mentioned. Weber fraction. So Weber fraction is supposed to be constant, as we have seen in the earlier graph. Here, only for a very small range, this Weber fraction is constant. That too in the photopic region. So when we come into the mesopic and the scotopic region, you can see that this Weber fraction is actually changing, and essentially it is decreasing from a large number, from the 70% or 80%. It is coming down to 2.5% or 3%. Okay, and after this region, you can see that the fraction starts increasing. So this is a small range where this is a range in which this is constant, and below this range, as I increases, del I by I decreases. This is modest. Yeah. And after this region, when I is increasing, del I by also is increasing. The slope is, so that the green line which talks about is the only log of del I. The change in the intensity, if you take the log, that is what is mentioned in the green line. The green line, you can observe that this is again, it is not constant. Del I itself is actually changing over the luminance. So this graphs captured the luminance over a very large area, a very large range, and you can see that the Weber fraction is actually changing. So both the extremes, there is a saturation and the dark light, where luminance is almost not luminance, this is the del I is almost a constant over here, this is almost vertical over here. In between, and you can see that the slope is actually slowly changing from 0.5 slope, and then it becomes 1, this slope, and then it becomes more, and this is another slope, it's 0.75, and then it increases to 1. Now when that light is perceived as a Weber fraction, and the graph shows, Stevenson law states the same thing in a slightly different way. As we mentioned in the last class, Stevenson law uses the magnitude estimation magnitude estimation, to remind you that the experimental task is to ask the subjects to give a number compared to a reference intensity in this case. So the y-axis is perceived. This is using the Stevens law. Okay. Y-axis is the perceived magnitude. X-axis is the physical intensity of light, and you can see that it follows a power law, and to measure the perception of light when there is an alternating patches of light of different frequency, such as like grating. This is a grating where alternating black and whites are displayed. Now in this grating, if you want to measure, what we can measure is the contrast threshold. So this alternating stripes as a grate is displayed in various contrast and shown to the subject, and then subjects are asked to check if they could identify the patches. As you remember from the earlier class, this is a psychometric function. X-axis is the grating contrast, and y-axis is the probability of yes answer, and this is the now yes curve. You can recognize this as a psychometric function. But the whole thing is for one particular frequency, frequency of grating. What if we change the frequency? The whole S curve will be changing it. The next graph shows how this psychometric function changes. Another terminology you have to learn in this course is this sensitivity. Sensitivity is nothing but 1 over the threshold. So lesser the threshold, the more sensitivity, more the threshold, lesser sensitivity. Sensitivity is one of the inverse of the threshold, we can say. So as the spatial frequency of the grating increases, you can see that until certain maximum the sensitivity increases and then drops drastically. In fact, this sensitivity, this is called the contrast sensitivity function, because it takes care of many grating frequencies. So this contrast sensitivity function has been studied for various photoreceptors separately. For example, photopic vision and mesopic vision and then scotopic vision people have identified. Both axes are in log. You can see that in the photopic and mesopic and scotopic, like the sensitivity function curve is vastly different. Now coming to the brightness, again we can either use Stevens curve or Stevens law or the Weber or Fechner's equations laws. Okay, suppose if you use x-axis luminous intensity and on y-axis is the brightness, that's the apparent luminance, then this blue curve shows the Weber-Fechner's law. In the literature you will say that Weber-Fechner's law together as mentioned as one name because Fechner is a student of the Weber. Okay. So Fechner used the Weber's equation to derive his law, so it is usually named as Weber-Fechner's law. The Stevenson law is usually mentioned as power law. You can see that the power law for rods and cones are mentioned as green and red separately. So Weber-Fechner's law starts with very high slope and then slowly saturates, whereas power law starts with lesser slope but it doesn't saturate as much as the Weber-Fechner's law. You can see that these two laws are from two different experiments. The Stevenson laws is using the magnitude estimation, whereas the Weber-Fechner's equation is using the JND. So you should see that these are two different tasks. So that results in two different curves. So the exponent of the cones and the exponent of the rods is given us over here. Both are less than 1. Then another psychological concepts as far as the light is concerned, that is the simultaneous brightness contrast, where you will see a light patch surrounded by another different contrasting light patch. Okay. The apparent lightness of the surrounded light patch will be different. That's a simultaneous brightness contrast. If you look at this graph, the center light patch looks different depending upon the surrounding. In the left image, because the surrounding is darker, the center patch looks brighter, and in the second right side patch, the same center patch looks darker because surrounding light patch is lighter. In the bottom one, you can see that the same light patch is used and it looks same in both the boxes. People have been wondering why. What is the mechanism for this apparent behavior? Many scientists have tried to reason it out. The same thing can be observed in many illusions. This is also known as lightness induction in many literature. You can see that the same light patch looks different, and it's a match bend where the light intensity is uniformly decreasing, but we can see that there is a small bend over here. In the Hermann grid, you can see that the same gray color, it appears white at the grid, at the 4 junction. What could be the reason? People have tried to reason it out. We will see whether that reason is correct or not. Our eyes, rods and cones, have this on center and off center receptive fields. Each of the photoreceptor has a receptive field, on center and off center. So those receptors that are completely falling on the dark side, their activity, let us say it is some quantity, let us say it is some zero level quantity reference. This is a reference. That are partially falling on the light field because they are all only negative of centers. So the spontaneous level of activity is actually lesser over here, and here equal number of positive and negative ganglion cells are fallen under both light and dark, so that will get cancelled, so it is back to the reference position. When more on centers are on the lighter side, then its spontaneous level activity is actually higher over here, and then more and more negative comes over here, so it starts decreasing, and then finally this reaches the uniform or steady state response of those photoreceptors falling on the light alone. Okay. This is the position we are talking about. This is the explanation which is given in most of the textbooks and research papers. But recently, researchers have found that this does not explain the simultaneous brightness contrast very well. One example is this one. Let us take this stripes of black and white and then vertical stripe of gray band. The gray band in the black, you can see how it is lighter when compared to the same gray band in the white background. So according to the on and off receptive fields theory of the ganglion cells, this should be resulting in the same, both should be the same, but it is not same. So the theory of receptive fields is not explaining the simultaneous brightness contrast very well. So researchers are still searching for convincing answers. If you are interested, you can go through this paper and find out more details about it. So we will stop here. So in today's lecture, we have looked at the fundamentals of the visual perception psychophysics. The psychophysics of visual perception is divided into, starting with understanding the physical properties of the light, the psychological properties of the psychological concepts of light, and then psychophysical concepts of the light. We looked at psychophysical concepts such as the contrasts and contrast sensitivity. We looked at a couple of psychophysical curves, datas from Weber's law and Stevenson laws, and then we compared them. In the next lecture, we look at some of the psychophysical concepts of color and the adaptations. If you remember, these are the three psychophysical dimensions of the visual perception. Color is a psychophysical concept, or chromatosity, in fact, is a psychophysical concept. We will see in details in the next lecture. The contrast we have seen in today's lecture. Adaptations we will see later. Thank you.